Hi Vananda. So today in this video we shall learn how to write the VHDL code for D flip-flop. More specifically we shall learn how to write the VHDL code for positive edge triggered D flip-flop. So first we shall understand what actually flip-flop means, and then we shall understand what is D flip-flop. Then after that we shall understand how to write the VHDL code for positive edge triggered D flip-flop. Clear? So at a high level, understand flip-flop is basically a memory element. Flip-flop is basically a memory element, and the capacity of that element is it can store only one bit at a time. So flip-flop is basically a memory element, and it can store 1 or 0 because the capacity of this memory element is only 1 bit. So hence a flip-flop can have the value 0, or it can have the value 1. Clear. And remember, this flip-flop usually it will changes the state from 0 to 1 and 1 to 0 on the application of the clock. So usually clock will be represented like this. So clock will have the positive edge. We call this edge as the positive edge, and we call this edge as the negative edge. So remember, once again I will repeat, flip-flop is basically a memory element, and the capacity of that element is only 1 bit. It means it can store either 0 or 1 at a time, and if you want to change the state of the flip-flop from 0 to 1 or from 1 to 0, you need to apply the clock. Clear? So this is a brief details about flip-flop. Anyhow, you will learn in depth about flip-flops and types of flip-flops in theory classes. So with this basic introduction, now we shall understand what actually positive edge triggered D flip-flop means. Okay, for that we shall assume this is the clock signal. Okay, this is the clock signal. Okay, clock usually will have two edges, as I said, positive edge and negative edge. We call this edge as the positive edge and the falling edge as the negative edge. So this is the positive edge of this clock, and this is the negative edge of this clock. This is the positive edge, and this is the negative edge of this clock. Okay, clear? This is the negative edge of the clock, and we have called this signal as clock. So this is one clock, and every clock will have positive edge and negative edge. Positive edge, negative edge. This is another clock, and this is another clock, right? And we shall assume this is our data signal. Okay, this is the data signal. Okay, this is the data signal. Okay, this is our data. Let us assume this is our data signal, and initially we have assumed the data is 1, then 0, then again it will become 1 and 0. So this is how we are providing, assume that this is how we are providing the input. Okay, clear? And now we shall take or we shall assume the D flip-flop has a value 0 initially. So our D flip-flop, I will call this content of D flip-flop as Q. Okay, Q. So because I will tell you why I have taken Q here, but there is no rule that you should take only Q. You can label that with any letters. Similarly, there is no rule that you have to label the data as data itself. You can use your convenient name. Even for clock it is true. Clear? Okay, initially we are assuming that Q has a value 0. Q has a value, I mean D flip-flop has a value 0. Clear? Okay, now interesting. Now we shall see what happens at the positive edge of the clock. So this is the positive edge of the clock, right? So this is the positive edge of the clock. This is the positive edge of the clock, first clock. This is the positive edge of the second clock, right? Okay, and this is the positive edge of the third clock. Clear? Okay, now see here at the positive edge of the clock, your D flip-flop will see the data. It will observe what is actually the data values. Now see here, at this instant the data has a value 1, right? And hence the content of the flip-flop will become 1, and it will stay in that one state, or it will have the value 1 until positive edge of the next clock. Again, at the positive edge of the next clock, it will see what is the data value. What is that data value here? Okay, again it has a value 1. And since the data has a value 1, it will reside in the same state, I mean 1 until the positive edge of the next clock. At that instant it will see what is actually the data, right? So now the data has a value 0, and hence the flip-flop content will be 0, and it will remains in the 0 state until until the positive edge of the next clock. And again at the positive edge of the next clock, it will see what is actually the data. If data is 1, then it will set to 1. If data is 0, then it will be set to 0. Clear? Clear? So from this discussion, we can say that D flip-flop is just following the data value, right? Right? And hence D flip-flop is also called as an data flip-flop. D flip-flop is also called as an data flip-flop, or D stands for data. Clear? And since in this case the flip-flop is changing the state either from 0 to 1 or from 1 to 0 depending on the data at the positive edge of the clock, right? At the positive edge of the clock, and hence it is called as an positive edge triggered D flip-flop. Positive edge triggered D flip-flop. Suppose if this flip-flop is changing the state, or it is triggering at the negative edge of the clock, means then that will become negative edge triggered D flip-flop. Clear? Negative edge triggered D flip-flop. So with this we understood what is actually a D flip-flop means, and we learned what is D flip-flop. More specifically, we learned what is positive edge triggered D flip-flop means. Clear? And anyhow you will learn in depth about the flip-flops, as I said already, in theory classes. Clear? Okay, now we shall jump into the VHDL code. Now we shall understand how to write the VHDL code for positive edge triggered D flip-flop, as I already mentioned in the previous classes itself. So first have a look at the port descriptions, I mean pin descriptions. So data is a single bit data. So we have data as an input, we need a clock. So again it is a single bit input, so we have clock, and reset is another input we are using just for our convenience. I will tell you what actually reset will do, okay, practically when we go to the tool. So for the time being, understand we need 3 inputs. Data is the actual data, and clock is the clock signal, and reset, this is also an input, and we are using this for our convenience, and I will tell you what is that convenience when we jump into the tool. Clear? And QB is just a complement of Q, and you no need to use QB as an output signal, just you use Q as an output. Okay, Q as an output, hence I have taken Q here for the discussion. Clear? So the bottom line is we need 3 inputs: data, clock and reset, and 1 output. We call that, we have labeled that output as Q. Clear? Okay. Remember in VHDL or in Xilinx design suite, whenever you are dealing with the flip-flop means you need to use a construct called process. And this process is similar to function in C or in C++ or in Python or in Java. Clear? It's similar to a function. So the general syntax of that process is, see, all should be in lowercase. So the keyword you need to use is process, and here this is the parameter list, and every parameter should be separated by comma. Okay, comma, and there is no flower brace here, okay, like in C or in C++ to indicate the beginning of the function. Instead there is a keyword called begin here, okay, which will indicate the beginning of the process, and here you can write any number of statements, and you need to end the scope of the process by using the keyword called end followed by process, and it should be terminated with semicolon. Clear? It should be terminated with semicolon. Can you see here? See here we are using process, and this is the beginning of the process, and here we have ended the process, right? And inside this process you can have n number of statements. Clear? N number of statements depending on the requirement. Clear? Okay, now we shall understand what actually we need to pass in the parameters. As I said, this is parameter, we call this as parameter 1, this as parameter 2, this as parameter 3 and parameter 4. As I said, every parameter should be separated with commas. Okay, and remember which are the parameters that we will have to pass in the process is, suppose if P1 value changes, and if you want to, if P1 value changes, and if you want, in that case, if you want to do, or if you want to take any actions, then you have to mention P1 in the parameter list, right? Okay, so that whenever the value of P1 changes, the actions that has to be taken will be specified inside this process. Clear? Similarly, when the P2 value changes, and whenever P2 value changes, if you want to take any action, then you have to specify P2 as a parameter here again, and where you actually will specify the actions inside the process. Clear? Are you understanding? It is very simple. So what are the parameters that we need to pass to the process? Means whenever the value of the parameter changes, and when the value changes, if you want to take any action in that instant, in those situation, you have to pass that parameter, variable as a parameter to the process, and where actually you will take actions, or we will specify actions for that case. It is inside the process. Clear? It is inside the process. So I will take a real scenario here. Okay, here we have supplied instead of data, here we have supplied clock and reset as the parameter. Why? Because whenever the clock value changes, I need to take some actions. Okay, those action, as I said, has to be specified inside this process, and here we have specified that action. Whenever the value of reset changes, again I need to take some actions, and those action has been specified inside the process. Clear? But whenever the data changes, I no need to do any or I no need to take any action. Hence, I have not mentioned data as a parameter here. Clear? Okay, now we shall go inside the process. So the meaning here is, this if keyword is similar to if condition. Okay, if condition in C or in Python or in Java. If reset, for better clarity you can also use this, if reset is equal to 1. See here, this 1 is a single bit constant, and remember, single bit constant has to be placed within single quote, right? And here this is actually assignment operator in C, but in VHDL this is a comparison operator. It means this operator is equal to comparison operator, this double equal to comparison operator in C or in C++. Clear? So this is in VHDL, this operator in VHDL is an comparison operator. Clear? You have to make a note on this. And one more important point you need to make a note on is, 1 bit constant should be enclosed within single quote. Like character constants, you have to enclose that within a single quote, and string constant you have to enclose in a double quote in C or in C++, right? So for a single character, single quote; for sequence of characters, double quote. Similarly here, when you are dealing with 1 bit, then single quote. Whenever you are dealing with multiple bits like 0, 1, 0, then you have to deal with, or you have to enclose that within double quotes. Clear? So these are the fundamentals that you need to be aware before writing the VHDL code for D flip-flop. Clear? Now we shall understand what is these statements are doing. See, it is straightforward. If reset is 1, if reset is applied, then assign the value 0 to the D flip-flop. Else if means it is similar to else if condition in C, but be careful with the keyword. Here it is ELS IF. It is not a keyword like else space if, like in C or in C++. It is a single word. Else if, see whether clock has been applied. 1 indicates positive edge of the clock. Okay, if you specify 0 here, then it will indicate negative edge of the clock. So since we have to simulate positive edge triggering D flip-flop work, here clock is being checked with 1. Clear? With 1. Then the content of the flip-flop will be assigned with the value that the data is holding. D is nothing but data, or just will copy the data value to the flip-flop in that case. Clear? So end the if block and end the process. So this will become the complete VHDL code for positive edge triggered D flip-flop, and I will convey now, I will jump into the tool now and I will tell you what actually reset will do. According to the code, just it will assign this value 0 to the flip-flop, and I will tell you why we are doing this. Okay, now we shall go to the tool. Okay, for the time being I will delete this. Okay, launch the tool, and as already told you in the previous class video itself, every project should be started with an, or every experiment should be started as a new project. Clear? Okay. Okay, file, new project, and you can choose as D flip flop, or you can give any name for the project. Okay, and every project should have one source file, and the type of that source file should be VHDL module, and you can give any name for that module. And here this is important, and I will call this as D for data, and CLK for clock, and reset, right, and Q, which is the output. This will be the output, and all these three are input, and I no need to use bus because all these are single bit data. Clear? Next, finish. So automatically the tool will generate the tool, and your job is you need to write the code between begin and end of the module. And as I already told you, whenever you are dealing with the flip-flop, you have to use a construct called process. Okay, and parameter list. Okay, then process will begin with an begin keyword, and it will end the scope with end process. It should be terminated with semicolon. And what are the parameters that you need to pass to the process? As I said, whenever the value of those variables changes, and if you want to take any actions whenever the value of those variable changes, then those variable has to be specified as a parameter to the process. Here, which are those parameters? Clock, then reset. Clear? Okay. Then what actually we are planning to implement the logic? If see that if reset is applied, I mean if reset as a value 1, then what you have to do? Then the spaces I'm giving for better readability or for better understanding, but there is no rule that you need to give this much space here. Clear? Then Q, I mean flip-flop should have the value 0, right? Then again for better understanding I am writing like this, else if. Okay, I will give one more space so that else if see whether clock has a value 1 or clock has been applied, then what you have to do? Then Q, I mean flip-flop should have the value of D, I mean nothing but data. So you need to end the if block with a keyword called end if. Clear? Okay, this will be the VHDL code for positive edge triggered D flip-flop. Remember, the process should be placed inside the begin and end of the module. Clear? So as usual, after this you can save the work. Okay, go to implement design, go inside synthesize XST and check syntax. Now compiler is checking for the syntax errors, so no syntax errors. Okay, fine. Go to the simulation part, then go to the project, new source, and you have to use the same test bench waveform for verification. Give any name for that. Okay, and even again don't worry about this, we shall see later. Okay, now see here, clock is one of the input and this is nothing but the clock. Okay, as I already said that clock will have positive edge and negative edge, and I can provide the data as I wish. Okay, data value, I mean D value as I wish. Okay, then remember, reset should be set in such a way that reset should be high initially, then low. See here, then completely low. Okay, I will tell you why, what is the reason of this. Okay, so provide the value for the data as you wish, high low. Okay, and remember, reset initially should be set to high. I will tell you the reason why it is so. Okay, then it should have the value 0, completely clear. And this is the content of the D flip flop. We no need to change the value of that Q. Clear? Okay, then save this. You will get a waveform. Select that, go to process, go inside the simulator, then simulate the behavioral model. Okay, this is the output window, and here you need to justify whether what you are getting is correct or not. Okay, see here, now reset is 1, right? Can you see here, reset at that instant is 1. So why initially we have set reset to high means to initialize the value of the flip-flop. I mean, in Q here we have labeled the D flip-flop as Q here to 0. Clear? So look at the code, that's what we have done here. If reset is 1, then assign the value 0 to the flip-flop, I mean Q. That's what it is doing when reset is 1. See here, even at this instant reset is 1, Q value will be 0. To start with a valid state, we have used an input called reset. This is the reason why we have used an extra input. Clear? Okay, then interesting, go to the positive edge of the first clock. This is the positive edge of the first clock, right? Approximately. Okay, this is the positive edge of the first clock, right? At that instant, what is the value of the data? Sorry, I think this is our clock, right? See here, this is the clock, this is the clock signal, and we are at the positive edge of the clock. Correct. And look at that instant, what is the data value? See here, this is the data value. What is the data value? It is 1, right? And hence, see here, Q flip-flop has been set to 1, and Q will remain in the same state. Can you see here, 1 until the positive edge of the next clock. This is the positive edge of the next clock. Clear? At that instant, again it will see what is the data value. Data is 0 now. Can you see here? Data value is 0. Okay, approximately. Okay, there will be a delay. Okay, no problem. There will be a delay. Okay, because that is the characteristics of the flip-flop. Okay, now I hope now it will be get cleared. So this is the positive edge of the second clock. At that instant it will see what is the data value. Data value is 0, right? And hence Q will be set to 0. Okay, like this we shall go to the positive edge of the next clock. Okay, positive edge of the next clock. At that instant, what is the data value? It is 1. And what will be the D flip-flop value? It should be 1. That's why it is called as a data flip-flop. Like this, you need to justify the result that you are getting is correct or not. Clear? So the conclusion of this video is, just in this video we learned how to write the Verilog code for D flip-flop, more specifically positive edge triggered D flip-flop, and we learned how to use the design suite to simulate and to verify the working of positive edge triggered D flip-flops. Clear? So with this I will end the session, and we shall see the next experiment in the coming videos. So thank you, Ananda.